I'm going to talk to you about explosive events, CMEs, which is an acronym for coronal mass ejections, flares, and substorms. That's a lot to cover in one talk. And so there is an overarching theme here, which is the theme of space weather. Each of the phenomena that I mentioned in the title have a very important role to play on space weather as we perceive it standing on planet Earth. Of course, in addition to planet Earth, there are other planets, there are even exoplanets, and certainly the considerations that go into space weather on planet Earth have implications for other planets and even exoplanets, as we heard this morning. But for the purpose of this talk, we'll focus on the heliosphere and planet Earth. And this is a cartoon that is familiar to all of you. Why I show it is because it has embedded in it all the features, at least qualitatively, that we will cover, certainly not to scale. There is sun, and as you know, when the sun is angry, it flares, it ejects material into space. It's most of the time in that state, known as flares, coronal mass ejections, which eventually arrive in the vicinity of Earth, where they interact with the Earth's magnetosphere, produce storms and substorms. And our ability to deal with all these phenomena in a predictive way based on data from satellites, be it through imaging or through in situ measurements, theory and simulations, is what goes into the entire field of space weather. It's worthwhile to begin with a few impacts of space weather. It is a rubric, in fact, that brings a lot of heliophysics under one heading. And it's not good to appeal to people's fears in wanting to do something in science. And I certainly don't mean to do that. Space weather, every once in a while, leads to extreme weather events that can have deleterious effect. But what is important to realize is those very dramatic events, which are rare, are not the only reasons why we want to study space weather. And this actually lists for you, beginning from the extreme events to less major events, for all of which it's important to study space weather. Extreme events lead to power grid failures, disruption to spacecraft operations. The energetic particles produced from these can disrupt electronics, diversion of airplanes from poles, radio interference. This is a standard thing. People are retuning their channels because the density fluctuations that come about in the Earth's ionosphere, for example, can lead to detuning. And radio operators, both in flight and ground, know about this phenomenon. Reduced accuracy of global positioning system, radiation danger to astronauts, disruption of telegraph services, and reduced efficacy of space wombat echolocation. You've seen this listed before, and certainly alarming things like that led some years ago for President Obama, I think, to look at a New York Times article and then actually ask the Office of Science and Technology Policy, which used to be an office headed by some eminent scientist, absent in the present administration, who actually initiated a major initiative into space weather. Obama was motivated by the desire to prevent major disruptions, even though he fully realized these are rare events. But since all of the power grid is interconnected, how major utility companies adjust to a major space weather event and make preparations was a thing that troubled him, and he certainly had asked his then science advisor to have a policy to set up that never really got completely implemented because we had a transition of administration. But certainly the work that was done then and put in motion led to a number of important developments that continue, and one hopes one will be picked up eventually. But as a classic example of the kind of event that worried people was this very famous Carrington event of 1859. It was also the first observed solar flare. And the associated coronal mass ejection, CME, took just 17.6 hours to reach Earth. Usually, such things take several days. This has a lower time scale. And there was, in fact, a previous CME prior to the Carrington event that sort of cleared the way, getting rid of some debris at the time and other things. The global effects, one observed Aurora at lower latitudes, and telegraph messages could be sent without a power supply. All of this in those days did have a major effect, but nearly not as much as it would happen if it happened today. This stands out as a classic event. People still go back and study it. But it's worth thinking about the fact that in July 2012, we had a near miss. And what happened was there was a major Carrington scale event that happened, but here is here is Sun. Here are the various planets, including our own fragile planet out here. And lucky for us that the CME actually went the wrong way. It actually impacted stereo A. Stereo A, and somewhat mysteriously, survived the impact because it continues. Yeah, I will take your comment.
We have started this conversation yesterday and didn't finish. And this is kind of an important area that we don't discuss often. So if you look at NASA spacecraft that have actually lived outside of our atmosphere for decades, meaning ACE, they are actually measuring this impact. So nothing really, no big calamity has happened.
Yeah.
Surviving pretty well. And in the case of stereo, so this question has at least made some of us think that, if you're inside the magnetosphere, the perturbation of the magnetic field and therefore the fluctuation is a lot more than if you are actually in pristine solar wave. The spacecraft wasn't more than
Yeah.
that's an area we should actually visit to, which we haven't.
Yeah, and on the other hand, the magnetosphere, I take your point, and that's a very important point because I certainly wouldn't have predicted that stereo A would survive a Carrington scale event, but it did, as she says. We are often told that the magnetosphere is a major shield for us. If we didn't have the magnetosphere, many of us would have been dead by now due to exposure to highly energetic particles that go through significant attrition before they arrive at our levels. So there are numerous things, numerous effects, some of it, as you say, are diminished by the magnetosphere and some that are amplified. Open question as to why stereo A really did this. Stereo B, of course, did not impact it, and you see these signatures. Stereo A did see very major rise in the velocities of the wind that passed by, whereas you look at stereo B and Earth, relatively unperturbed. So this was a space weather event that also needs further understanding. Having said that and emphasized to you how a major solar event could have important space weather implications, I now want to break up the discussion into a discussion of the important attributes of coronal mass ejections, flares, and substorms. I'd like to connect them through a thread of possible mechanism, which is by no means definitive and is an answer to everything. But certainly, as you will see, that it is possible for current sheet formation and magnetic reconnection to play an important role. Whether it accounts for all the signatures that we see, we do not know. There is a lot more complexity to these things than just waving one universal mechanism and throwing it at all events. But certainly it's an important mechanism that merits attention. So here it is, we first start with flares. No doubt that magnetic energy is released suddenly. There is efficient plasma heating and particle acceleration as a consequence of it. And the energy which is released somewhere above the corona is transported down to the chromosphere, where it also results in energetic particle beams and or thermal conduction fronts. And when I show you the cartoons, you will see how this all fits in probably in some sort of a classical model. And the radiation emitted can vary from radio, which is very long wavelength, to gamma rays, which are short wavelength. This is phenomenology. We have not done any theory yet. But this we all agree upon. Observationally, there's ample evidence. And thanks to Solar Dynamics Observatory, which I hope is an app for many of you on your iPhones, you see spectacular events like this, which absolutely beautiful in the eyes of the beholder, and to be able to predict these things from first principles theory and simulation would be a great goal, except for the plasma parameters that characterize such events lie well outside of the scope of all codes. So we have to learn to accept where we can go right now, but these are the challenges we now face. How do we account for beautiful phenomena like this with theory, simulation, understanding? That's as far as flares went, and I deliberately showed you that event because it actually ties up with a particular aspect of solar flares that is worth emphasizing. It is that solar flares operationally are sudden brightening in X-rays, and when you look at this, there is a big peak here, and there are two things you notice. One, it's in the company of many events, large and small. And the movie that you saw with SDOs was just not one peak. It happened at various levels of amplitudes, and you also saw a very large one at that. And if you bin the sizes of all these peaks, what you will find, in fact, is that there are large events and there are small events, and all of them have one universal character about them. They're all impulsive, a certain impulsive character to them. A period of quiescence, and then a sudden change. So if you're thinking in terms of instability theory, where we say we need a rapid growth rate, a gamma, like the one that Nick was asking you to calculate out of a time evolution equation. What is interesting about these events is a subtler thing. Gamma changes. Gamma can be small and then become large. So for a theory to be truly predictive, it has to predict all phases. The slow phase, a quiescent phase, and a sudden change. In other words, it's not enough just to have gamma large. It's important to have d gamma dt change suddenly. That's a harder burden on theory, and certainly tells you that it is probably outside of the realm of linear instability theory. Because in linear instability theory, you start out with a certain given equilibrium, you linearize your equation, and if there is an instability, you get a growth rate. That's your number. But this, that you see an impulsiveness, means that that gamma must change. So something in the background must be evolving on a slower time scale as well. And keep this in mind. Don't be fooled by impulsive theories, no pun intended, which just give you one number. Tell them that there is at least 2 time scales in the problem. And this is common between flares, CMEs, as well as substorms. I certainly take this as a burden for me to work on. And if you look at this thing, that the event frequency, and if you're binning things according to their sizes, green being large, orange somewhat lower, and blue lower, you see that the events that happen 1, 4, and 11 in this particular sequence are all happening within a day. There's also a very complex phenomenon. And what I want to emphasize here is that it takes a lot for a theory to be able to give you this time sequence. And when Madhulika kindly offered to say that she was going to tell you about deep machine learning, I thought that this is something that you should think about in addition to thinking about plasma theory and simulation. Because we have a wonderful database, and can we, on the basis of deep machine learning, make sense of events like this to see what are some of the salient features that we need to understand from physics-based models. So in a way, perhaps because of the efficacy of modern computational tools, we can bring both such approaches to bear. But I won't talk about the second part of this sort of a thing. That will be the subject of the next talk. So mine is much more of a physics-based talk, but keep this in mind. There's no theory I know at the present time that can account for this complexity of time scales, of multiple events of various amplitudes. So theory and simulation is a much more modest enterprise at the present time. If we can explain one of these major peaks or a couple, then we think we are doing quite well. And the sense is that somehow if we could learn very long-term evolutions of such systems, which is very hard to do because you have to get the rapid time scale and the slow time scale of evolution with multiple events occurring, you're really looking at very, very long computational cycles. Then in first principles codes, they're beyond the range. And yet you have to be predictive about space weather. Keep in mind that every stage of our evolution, that is what we have to do. So we need to use our computers as well as our codes for physics-based understanding based perhaps on intelligent machine learning systems that will teach us a lot about patterns and so on and so forth. I want to now talk about the salient features of coronal mass ejections. I'm sorry that my talk is going to be superficial, but I hope you will view it in the larger context of space weather and where each of these types of events fit in, and realize what the challenge is for the strategic capabilities, the computational capabilities that we now have to be truly predictive for weather. And just in meteorology, we are gradually getting better and better with weather, and our codes are getting better and better from short time to longer time scales. One hopes we'll get to similar place with space weather. Coronal mass ejections, discussed as a separate topic, have somewhat different features. They actually involve the expulsion of magnetized plasma into the solar wind. This can be a very massive ejection, genuinely a tonnage thrown out for the sun. That's not necessarily one that the flare requires, not at all. In fact, this led to an interesting discussion on CMEs or flares and which affects space weather. This has velocities of the order of hundreds to thousands of kilometers per second. Usually it contains a large macroscopic structure, often known as a flux rope. What is a flux rope? It's a toroidal plasma which is threaded by magnetic fields. And the magnetic fields have a component which is axial and a component which is poloidal. The combination of the poloidal field, which goes around the short way, and the axial field, which goes the long way, gives the magnetic field a helical twist. And as you move from the axis of the torus to the edge, the shear of the magnetic field changes. That's the distinguishing characteristic of what is called a flux rope. And oftentimes when you look at coronal mass ejections that are ejected, they often contain a flux rope. And a shock precedes the flux rope, which can accelerate particles. And these CMEs are in fact the major drivers of geomagnetic storms. The flares, though, don't forget, they're also very major magnetic events that throw a lot of energetic particles out into space. And as we will see, some years ago, there was a major controversy in the space community about CMEs versus flares and what causes major geomagnetic storms and doesn't, and how different are they. Jack Gosling, who recently passed away and who made many striking contributions to space physics, wrote this paper on the so-called solar flare myth. But I'm happy to tell you that we have left all of that behind now. I think we understand much better today, thanks to his contributions and of many others he stimulated, what are the major drivers of geomagnetic storms. And so CMEs are this. And by the end of this talk, I will attempt to pull CMEs and flares together in the context of one model so that you can see that as the development of a standard model, if you will, which will have both in it. But this is the distinguishing feature of CMEs. Now, once the CMEs and flares are actually hurtled, the CMEs towards planet Earth, the sun sends high-velocity magnetized plasma, solar energetic particles, and/or UV and X-ray radiation towards Earth. Then what? Well, the particle and plasma components impact the Earth's magnetosphere. The UV, X-ray radiation, and particle component, which can be contributed equally by flares as well as by CMEs. In the CMEs, the shocks that precede it can also accelerate particles. And these components affect the Earth's thermosphere and ionosphere, causing their major perturbations. Magnetic field fluctuations, electric field fluctuations, flows, density fluctuations, and so on and so forth. You're looking at a very complex system driven by major events on the sun. And so this is our beloved magnetosphere. So imagine the object comes and hits planet Earth. Solar wind particles can get in through reconnection events that occur due to the interplanetary magnetic field, which is swept in, reconnects with the Earth's dipole field. Why did this do that? And what happens is that flux gets transferred from the left side, from the sun side, to the other side of the Earth. You have the Earth's magnetotail that narrows down, thins down, and in fact sometimes thins down to size of about half Earth radii of the order of a Larmor radius or an ion skin depth in plasmas. And you have thin current sheets that go through very major dynamics, one of which is reconnection, but by no means the only one. And this complexity of dynamics eventually leads to triggering of substorms, which lead to aurora of the kind that you see often in Alaska. If you get up in the middle of the night and you're lucky, the sky brightens up. And this too occurs in impulsive, sporadic ways. So the impulsiveness or the time dependence of the growth rate persists in all of these phenomena. Flares, CMEs, or substorms. As I mentioned, if I'm going too rapidly, stop me. You're all with me, right, so far? So far, quite qualitative. The Earth is not alone in auroral phenomena like substorms. You see them in Jupiter as well as in Saturn. In fact, Chandra, the astrophysical observatory, produced some spectacular pictures of substorms. Don't have time to go into that. We have also had flybys of satellites that have gone through. Galileo, for example, provided some wonderful flybys of substorms. We have data from it. So there are planets with magnetic fields generated by dynamos and otherwise, have their magnetospheres. These, in fact, are impacted also by the solar events that I'm talking about. and produce their own versions of storms and substorms. So if you understand this in the context of our planet, chances are reasonably good that we might understand them in the context of others. I now want to get into I want to take a step back and say, so you know what CMEs are, what flares are, and substorms are. And now I want to get into the physics of these things to the extent we can. A set of models that began from simple considerations for flares and CMEs and have led to what we call the standard model of CMEs and flares as we understand it, can be begun from this work of Terry Forbes and Philip Eisenberg at the University of New Hampshire, been developed further by their students and postdoctoral fellows as well as their colleagues. Let me tell you what this simple model is about. You can start with a vacuum field, curl B equals 0. You can solve that easily, as Dana was telling you about on the first day of this summer school. And it turns out to be, even though unrealistic, because we know that the sun has plasmas and this field is not strictly a vacuum field, but nonetheless is a great point to begin, because given the vacuum field has features in it that are relevant to the more complex problem. So imagine now you start out with a two-dimensional field, and imagine that this is your photosphere. You start out with a vacuum field, there's no current density, but the photospheric foot points move, driven by internal motions in the sun, as you well know, and on the surface, as a result of which you can, in fact, produce current densities. And what was interesting about the model of Forbes and Eisenberg, developed further, was that in this very simple model, you can calculate the energy of this state, and then as you move it around, you bring these foot points closer together. They demonstrated that there is a lower energy state represented here, where there is in fact current density in the form of an extremely thin current sheet, shown by this energy curve, where magnetic energy is been calculated as a function of the height of this current sheet as it rises. And what you see here is that you drive this, it goes to a minimum energy state, goes higher as you're driving it, and then falls to a lower energy state. This lower energy state actually is sort of a bifurcated structure, if you will, that beyond a critical point, try to jump to this state, not go through this path. So you have two states available to the system, one without a current sheet, vacuum field, another with a current sheet structure. Believe it or not, you might say, there's a singular current density sitting there in the middle of it. How can that be a lower energy state? It's counterintuitive, I know, but it is true that sometimes systems with thin current sheets in them, where the flux outside is much lower, has lower energy than the ones that you started out with. The question is, how do you access this, and what happens to this thin current sheet? This is a long and subtle story. But once you set up, this is ideal MHD. You have no dissipation in the system. But you know this from my talk on the second day, that what magnetic reconnection does when you form very strong concentrations of current density is to potentially break field lines. And there will be a tendency for this object to just be thrown out into outer space with this current sheet being pinched by reconnection and separating out. You therefore have in this model a mechanism by which you can start out with build up energy into the system gradually by footing foot points, and it rises from the vacuum field, goes up higher in energy. Then it forms a quick bifurcated structure with a thin current sheet that will get nowhere if it just stops at that level. But if you have some dissipation, the current sheet can be pinched off, and that flux tube can be thrown off. So this you could think of tentatively as a model for a coronal mass ejection, provided, of course, nature cooperates with you in providing dissipation there, which you would presume is a reasonable idea. But sometimes what happens is that on top of that tube, you have larger strapping fields that hold the thing down. So in order for the coronal mass ejection to truly break through, it must find a way of getting out over the strapping fields. And I'll comment on that, on how the plasma might do that. But here is a picture we actually did. You'll say this is all a figment of the imagination. And what about plasmoids that I have been talking to you about? Well, that thin current sheet will have a tendency to break into plasmoids. So if you run a sufficiently high resolution simulation, and we actually did this with this particular configuration, and truly enough, you see tend to break up into plasmoids. And you see this motion. Think of the movie that you saw when I showed you this talk Tuesday. Formed this thin current sheet that broke up into plasmoids, flows. You're having similar things go on here. And these plasmoids are going to get ejected. And what we did here, this is actually work done by my former doctoral student, Ligia Guo. She right now is in Lockheed, working with the IRIS instrument. She actually wrote a synthetic diagnostic code trying to count the emission profile from an MHD code like this. So you run the MHD equations with high Lundquist number. I won't repeat all this because I know you're masters of MHD now by this time. So you form these plasmoids and you can get these structures. And she did more. I want to point out to you that this whole idea that a thin current sheet breaks up into plasmoids was in the literature before we understood what these plasmoid instabilities are. It's by Shibata and Tanuma, very nice paper, 2001. Look at this cartoon. They got the picture. They called it fractal reconnection. 8 years later, we made this theory much more quantitatively precise, and I was not even aware of Shibata and Tanuma's paper. I learned it from our simulations, but it was there in their work. They got all the growth rates and everything wrong, but they had the right picture. And the picture was this of what they call fractal reconnection. They argued that a thin current sheet would break up into this sequence of plasmoids, self-similar structures. In other words, if you take a small segment of it and you blow it up, you'll see structures in it that are very similar as they are in the larger thing, be that as it may. And in fact, we calculated what will be the distribution function for these plasmoids, because they will be in various sizes, large and small. The thin current sheets become unstable. You form these bubbles. Then these bubbles coalesce to form the large ones. The large ones hang around longer than the smaller ones, which get cannibalized by the large ones. And so if you look at the magnetic flux contained in them, just B dot dA, that's psi. How does the plasmoid size distribute itself according to magnetic flux? And you see, in fact, they have a power law. They obey something like 1 over psi. You can calculate that. So I went back to the CME current sheet, and you could ask me the question whether we could, in fact, count plasmoids. So Ligia Guo focused on this problem, and good work was done in this by David McKenzie, other people at Montana State University as well. And they had, in fact, reported log normal bubble formation. They're looking at these current sheets, and we cannot measure coronal magnetic fields by in situ measurements in the sun. I mean, Solar Probe Plus or the Parker Solar Probe will get as close to doing that as any spacecraft has ever done. But mostly, unlike the Earth's magnetotail, where we have in situ probing, magnetometers and otherwise, everything we know about the sun is through images. And so if you allow us the luxury of thinking these blobs are what are plasmoids, how do I know? I don't really know, but let me make that big assumption. Ligia did this, looked at Alaska data, and she counted 72 plasmoids, very persistent person. And she actually plotted this plasmoid distribution. And one of the things she found was she and a bunch of her friends did a naked eye test, and then they did it within a simulation code, that they first counted plasmoid by just eyeballing it. And then what they did was they went to their MHD code and actually wrote a more precise diagnostics through inflection points in the flux function and counting those plasmoids, assuming that you know the magnetic field with great accuracy, which is given by an MHD code. You can count it two ways. Have the code count it for you, or you can count it with the naked eye. She found the results were different. In the realm of small plasmoid sizes, in fact, the code gave us this distribution where Mackenzie, Savage, and others were actually talking about more like the plasmoid structure coming down at lower wavelength, going down this. Remember the power law I was showing you from our plasmoid distribution? It was a power law. It went in like that. And Ligier concluded from this that this was an artifact of undercounting. When you do things with the naked eye, you just don't count the small plasmoid. But if you're doing a simulation, then there are small size plasmoids, and what you're really seeing is this exponential curve. So you can say, what happened to your power law? Stirring range, power law, and then exponential decay. What she concluded was that the spatial resolution of the instruments was such that we barely see any of the power law at all. It's all the exponential tail. This does motivate you to have missions which will actually be able to resolve this with higher level of spatial accuracy. A challenge for solar coronal observations, nonetheless one that they're meeting more or less. And this is what we were doing here, is to actually count it two separate ways, plasmoid scale distributions from synthetic diagnostics in the code and from the naked eye, and you get different distributions. Naked eye confirmed the Mackenzie-Savage results. The code diagnostics actually told us that this part of it was probably due to undercounting, and we are really part of this exponential thing. I went into this in some depth because I don't want you to think we all live in imaginary land. We make up all these models, and there's no way to test it. There are ways to test some of these things, even for the sun, when we can probe it. Now, I want to get back to this whole issue, that imagine this Forbes-Eisenberg model gives you the rudiments of how you start out with a vacuum field even, photospheric foot-point motions, produces then this sudden jump to an equilibrium with big embedded thin current sheet, which can then go unstable. But can this bubble escape? In the 2D calculations I did, this is done easily. Just snip it and it'll go. But this is not what happens in the sun, because the sun has trapping fields, three-dimensional fields that break the symmetry of the simulation models. And you need more drive to get that coronal mass ejection to go beyond. And this is a simulation of Turok and Kleem. I'm getting annoyed with this. What's the matter with UCAR? It doesn't allow me to stay focused on my talk. I did nothing different, but I don't know what's happening. But so look at these pictures, very beautiful pictures of CME, and what you have to understand that this is really a three-dimensional torus instability. So two-dimensional models will not completely capture it, but people have actually done these three-dimensional ideal MHD simulations. I was talking about reconnection paving the way for actually ejecting these two-dimensional structures, and what you need is a combination of two things. Reconnection, of course, to help you liberate the energy you need and to break off these structures, but you also need the help of three-dimensional ideal MHD drives, kinking drives, if you will, of the kind modeled by Turok and Kleem here, where they're trotting out with a flux tube which twists, and it can go through that reconnection and the structure in a way that you actually perceive, but then will break through the strapping fields and escape. So you need a combination of reconnection, ideal MHD instability, to actually come to an understanding of flares as well as CMEs. Now, flares can occur. I want to get to this. So this is another simulation picture, and now I want to come to trying to tie this all together in one overall picture, what we call the standard model. In the standard model, what happens is, and this I would call this a basic picture, because you can see our efforts as trying to build this up from 2D to 3D, energetics, mechanisms, and we cannot claim that we have all the realism in one model that does everything perfectly for the plasma parameters that are relevant. This is still a distant dream. But the pieces are coming together, and observations would provide stringent tests. So here is the sun. Even if you started with vacuum fields, you will soon form this current sheet structure, because it would tend to form this structure driven. Then what will happen is that you get this big CME structure. The flare occurs at a somewhat later stage of a CME ejection process, whereby flows come in, heat is conducted, and the flare actually occurs in this region. So CMEs and flares in this model are sort of interconnected in one complex picture, with the CMEs occurring due to the ejection of this major thing going up. And here you have flares occurring at the foot points when you have plasmas coming down, energy is transported, and then you get this current sheet forming into between this large structure up here and the magnetic arcade sitting below. And as a result of which, you form both of these. So if I may put together, yes. Yes. Right.
So if that happens, do we expect to have the same flare up because also it goes the other way?
Yes, you could, in principle.
But your point is flare happens after CME in this picture.
Right. In this picture, it actually occurs in the sequel. And so as I was just going to enumerate this, here, in this picture then, there are the following ingredients. First, you develop a flux rope, and even if it is a vacuum field or a force-free field, you start with that, a very low energy state. Then you start twisting the foot points with the photospheric motion. That builds up energy into the system. That building up the energy is important. That's in fact the quieter phase, when things are happening more slowly, building up. If you get reconnection too soon, and that's actually a problem. In the plasmoid picture, I want to point out to you that it's one of the unsolved issues that we have to wrestle with, which is that if the plasmoid instability is too easy, then do we have enough time to build up energy before the energy is actually removed? Sometimes in a flare, you wait for 20 to 30 minutes to build up, or even days. 20 to 30 minutes is too small. It's probably more appropriate to the magnetospheric substorm. In flares, you wait longer time, and then you have a sudden eruption. So we have to make sure that we have this storage of energy time. The increasing twist can lead to instability, as you saw. Take the example, the Torok-Klein simulation that I showed you. The eruption converts energy from magnetic to kinetic. The frozen flux, the ideal MHD evolution, produces this current sheet. But if it were only for ideal MHD, we would form that current sheet. It will be a saturated current sheet and will go nowhere. You need reconnection to have that process go further, whereby the stored energy will have to be released. That's where reconnection occurs. At the current sheet, eliminates overlying flux, can lead to instability, can permit further eruption, and will produce flare signatures later in this model, as you just said, as a sequel to this. I do not mean to suggest that this is the only way, the only sequence of events that does this, but this model has the nice feature that it does provide a unifying thread to many disparate things. I want to get to the Earth's magnetosphere. Yeah?
So are the flares and CMEs always related to each other? So, I mean, if there's a flare, do you always have a CME?
This is actually a really good question. CMEs are often associated with flares. Flares, Dana, would you comment on this? Are all flares always associated with CMEs?
No.
So,
Unfortunately, there's no 100%.
yeah, exactly. Yeah, and this is what actually led to the Gosling paper that I was referring to you earlier, which one thing is clear. People do agree on one thing, that CMEs are the major drivers of storms or substorms. But let's not forget, that's not the only thing that happens in a major solar event. Energetic particles are produced equally effectively by flares as well as CMEs. And CMEs, in fact, because of the intervention of shocks, you have an additional source that rise. Yeah?
If Jan Swicker were here, he put his hand up and say, and flares drive the ionosphere too.
Oh, absolutely. Sure they do. Okay. So I want to get to, in the remaining time I have, which is about 15 minutes, because I do want to give you a break before Madhulika's talk. I want to now get to substorm onset. And you remember I said that what happens due to, are you guys with me so far? Not going too far too quickly? Anyway, a bit of it is inevitable. So you have this big magnetic field that is swept in, the interplanetary magnetic field, that connects with the dipole magnetic field, produces reconnection events on the day side, sweeping flux to the night side, a gradual thinning of the plasma sheet, as I was telling you. And the canonical picture is that at distances about 35 to 40 Earth radii, you produce a neutral point. That this actually occurs is incontestable. Geotail, which was a major mission, did tons and tons of statistics to actually make this point, that at 35 to 40 Earth radii, as a gradual evolution of the system, you really do have this. But that's not the primary problem of the substorm onset, because based on auroral observations, people know that the formation of that neutral point, while it is very important, and Professor Slavin here is an expert in these sorts of models, which are known as the near-Earth neutral line models and other models of substorms, but at least I want to pose the problem for you, which is that it is not contested that you actually, because of the gradual thinning of the current sheet, that eventually the normal magnetic field, which kind of gives the field a parabolic structure, becomes small enough that you will get a point where the field goes to zero. But what really happens is, and I think observers agree on this, that the real onset of the substorm, which maps on to the Earth's aurora, occurs at distances that are much closer to planet Earth, about 10 Earth radii roughly. It's 10 or 15 is a matter of debate, but definitely not mid-tail distances. And even back in 1992, when we didn't have multi-satellite observations, Otani was putting forward this interesting evolution of what he called the cross-tail current density. Very ingenious set of observations. And this has been also verified now by Themis, which went up more recently and get observations. And I'll show you some data from that. But Otani argued that you actually have a slow growth phase lasting about 30 to 45 minutes, then an impulsive growth of the current density to very high values, and this is typically at a distance about 7.8 or 10 RE, based on really old data, and then a disruption phase less than 10 seconds. What you're looking at in this picture is a multiplicity of time scales. And I like to remind people that substorm onset also has this impulsive feature, this multiple time scale, which should be a constraint in all theory models. It's not enough just to get one rapid growth rate, as linear theory gives you. You must account why there should be a slow growth phase. It holds the key to substorm onset, then a rapid onset, and then a disruption. So at least 3 time scales. And we know this now from data. Have this constrain your theories. Sometimes I think theorists get too happy because I do not know of one theory that actually produces 3 time scales correctly. So I'm going to tell you, therefore, that it remains an open problem. Themis actually fortified the Otani picture because they had a confluence of multi-satellite as well as ground-based observations. And what came out was this sort of a sudden onset wave. Your hands went up. Yeah, good that you asked me. I didn't introduce the coordinate system, did I? Because, see, these are GSM coordinate systems that magnetosphere people like a lot. XZ is the plane that you're looking at, the plane of this wall. Y is the coordinate perpendicular to it. So you're looking at the current density out of the plane of the paper as it is building up. So the thin current sheet that I was telling you about at these distances is a very thin current sheet. The current density is pointing out.
So this is, you are looking at the night side?
Yes, at the night side. Okay. So I want to show you some auroral pictures. These are classical pictures of this. This is from my former colleague Lou Frank at the University of Iowa, where I spent many years. I was fortunate to spend many years with Gurnett. Frank and Van Allen was also around in those years, and they were great years for me to learn magnetospheric physics, which is where I picked up most of what I know today. But he had some spectacular pictures of, by using camera, of the way in which the aurora develops. And this is, both of these gentlemen are now gone, but their pictures remain with us. And what happens is that you see a sudden intense bulge in the auroral oval, signals the start of an auroral substorm. And you go on and you find that it forms close to what is called the midnight sector. This superposes the overall geographical map of the Earth on this picture. These are real observations. This is no cartoon, by the way, and this is really an example of what wonderful magnetospheric observations we have which constrain our theories. What you're seeing here is this poleward expansion. You see this? And this enormous brightening. These are very impulsive events. From here to there, that happen very quickly. And then it gradually fills out and decays away. So theory of substorms has to account for all of this. So I want to tell you what the theory of substorms right now is at. What do we know? And I won't be able to tell you all the great things that have happened, because thanks to observations, a lot of developments have happened that are very promising. But I cannot say that the picture is complete yet. Some people's minds it is, but in my mind it isn't. Because remember my 3 time scales? I seem to be the last person on Earth who seems to worry about all 3 time scales. But in my mind, I do not have an explanation to you for all these 3 time scales. So this is how the picture is built up. So there is a cartoon of Earth. You are asking me day side or night side. I'm developing it in the night side. And the tail has become thinned out. And because of the tail is thinned out, the dipole field is also getting stretched out, thinned out. And out at mid-Earth distances, you get this X-line formation. This is a classic signature of magnetic reconnection at mid-tail distances. Between 20 to 30 RE, and I'm saying to you this much, that the substorm community, nobody argues about that one anymore. Then you have flows coming that occur due to the result of reconnection. But right when these flows arrive here, you get a lot of flux that piles up. What exactly triggers at distances about 10 RE the onset of a substorm is a matter of some debate. There is no doubt that reconnection must play a role, because after all, you're going to liberate all this energy and eventually plasmas are going to get thrown out. But the question is reconnection producing that? Or is it that the flows produce enormous intensification of local pressure gradients that drive Rayleigh-Taylor type of instabilities? In this case, actually a coupling between pressure and curvature, known in the plasma physics literature as ballooning modes. If you look at ballooning modes, they have very interesting properties. And I don't have the time to go into it. They start out with a linear ideal instability. But as they grow, they produce fingers and thin current sheets in their wake. And these thin current sheets can then go unstable to reconnection. So it's clear then that in order to fully understand substorm dynamics from a slow phase to a sudden explosive phase and a decay phase, we must have simulations of theory that couple high pressure-driven ideal MHD instabilities of the type that these ballooning or Rayleigh-Taylor instabilities are, with reconnection events, which for the longest time was put forward as joint mechanisms for reconnection. And what observations have done for us is to refine this picture further and provide us, I'm getting tired of this, fill this picture out for us and give us more constraints. One of these, for example, I mean, this is from clustered data. You know, this is not at substorm onset, but it's in substorm onset times. Li Jian Chen published this, and she was a postdoctoral fellow and my colleague, and now working on the MMS data, which is a very, very exciting mission. But this came out from our cluster studies. What she actually found was the Earth's magnetotail, thin current sheet, is spontaneously unstable to a lot of plasmoids. Not just one, but multiple. And in fact, she did a lot of detective work with cluster spacecraft. And one of the signatures she looked for was the so-called BZ. Remember, this is X, Z, Y is perpendicular to the plane of the paper. And so if you're looking for islands or plasmoids, one thing you can look for is that there's large BZ regions and there are small BZ regions where you have X points. She did a lot of detective work with simulations, using particle and cell methods, and all of this. And she came out with this very interesting picture that you get highly energetic electrons coming out of these plasmoid pictures. And see, she saw like 10 islands within 10 minutes. And what she's reporting here is the electron energization at multiple islands. And you see these peaks, and you see all the energy channels. And her interesting observation was that the largest densities came not from the X points of the islands, where the electric field can be the largest, but from the O points of the island. By O points, I mean the central structures, like here in the middle. That's where the peak density. So at the X points, you get a lot of energization. You get high energies. But if you count the numbers, the larger numbers come from the center of the island. So something is going on within these islands. And this is probably the kind of physics that we need to understand that Jim Drake put forward, where he actually said that in order to understand particle acceleration in these systems, it's not enough just to rely on thin reconnecting layers, because you get into a numbers problem. Like in solar flares, there is a well-known numbers problem put forward by Bob Lynn, Sam Crooker, and others, who looked at RESI data to tell you that when you have a solar flare, roughly half of the electrons in the plasma volume are accelerated to very high energies. And if you're relying on narrow reconnection layer to do this energization, it's not enough. You need something more. And Jim suggested that probably due to a production of a large number of islands, though he didn't know the plasmoid instability at the time when he put forward this idea. That came later, but what we're telling you is that maybe the plasmoid instability provides a copious source of such things, trying to explain observations like Lejean's, which shows major energization at all levels of energy, the largest numbers coming from the center of these large islands, which are much broader than the thin current sheets and hence more visible. Think of the solar picture that you had, these plasma blobs, those islands. You can't see the thin current sheet, but you are being able to see the islands. So similar things are going on in the Earth's magnetotail. Mystery persists. So I'm going to move on. I have to tell you a little joke about, this is Kamide's joke about the so-called 2-minute problem. I tell you there are many things we understand. This was an April Fool's joke that was made up by Chris Russell, I think. And he wrote this out at the end of a substorm onset. And I'm sorry to say that the joke still has validity. And it says, this year's substorm conference was one of the most successful yet, with over 250 in attendance. This is typical of the ICS substorms. All existing paradigms were discussed at length, and during the wrap-up session it was realized that only the time of the events within 2 minutes of the onset were still seriously under debate. Ballooning, reconnection, maybe the two, one or the other. Some people think it is this instability, and some other guys say it's this instability. And you look at the two camps, these are entrenched people who've been saying the same things for 20 years. And the younger people are the ones, you, who are open-minded enough to go out and say, maybe it's a combination of the two, who knows? So he says, since it seems somewhat foolish for a couple of hundred scientists to travel halfway around the world to argue over 2 minutes of geomagnetic activity, the substorm problem was declared solved and no more substorm conferences are being planned. Well, I just want to tell you, I attended ICS 13 in New Hampshire, and we're going to have ICS 14 as well. So this was an April Fool's joke by Kamide-san, always known for his ready sense of humor. But just to let you know that you still have time to make contributions. So I want to leave you with some open questions. Open questions which impact each one of these disparate events I talked to you about. Trying to synthesize all of them to make a space weather picture remains a challenge. And I hope you will take up us all on it. And I hope that the lectures in the summer school is giving you a glimpse of what some of these problems are. How do solar and planetary dynamos operate? You've had a lot of really great ideas discussed here. None completely conclusive yet. How are the chromosphere, corona, and solar wind heated? What accelerates the slow and fast solar winds? These were the dynamo talks. This is Stuart Bale's talk. How does reconnection release magnetic energy in solar and space plasmas? Can we predict major flares and CMEs? If you know the magnetograms and you get more and more data, are we ever going to be in the position where we have all this stuff that is driving our simulation codes? Can we predict them? Can we predict if and when ejecta and energetic particles will impact Earth? How can we predict the direction of the interplanetary magnetic field at Earth using remote observations? How frequent are super flares on the sun and other stars? How can we apply results from space plasmas to astrophysical plasmas and vice versa, I should add. Thank you very much for your attention. Take a break. Next talk will be 2:15, but before you go, you can take 10-minute break if you have any questions. Yeah. No, because you're right. And in fact, you know, that they're looking at purely ideal MHD instability there. I think PPPL, we had a graduate student who looked at the torus instability in a laboratory context, and he published a Nature Communication paper on this. And he pinned down, using laboratory measurements, what that index has to be for the torus instability, and found, in fact, that the predictions that were made for some of the existing simulations are not in accord with these observations. That does open up a problem. Ideal MHD theory, in the form it was being exercised, doesn't seem to explain the observations on MRX. So I don't want to give you the impression that that's a solved problem either. There's some discrepancy between control experiments. But you're right to, and it doesn't appeal to reconnection at that point. Any other questions? If not, take a break. Thank you very much again.
So, first or second ICS, Charlie Kennel was the one that formulated